today's topic is Fibonacci method. This method is again another elimination technique for solving single dimensional one variable nonlinear optimization problem. The basic necessity for applying this method is that the function must be unimodal in the initial interval of uncertainty. Now, one thing must be said that this Fibonacci method, the beauty of this method is that it makes use the Fibonacci numbers in the sequence. That is why there are certain limitations of this method as well. Now, let me just first tell what are the basic necessities and what are the limitations for the Fibonacci method. First of all, this method is an elimination technique. Elimination technique, that is another name can be said as the interval reduction method for solving for getting optimal for nonlinear optimization problem. And the basic necessity for applying this method is that, as I said, this is the basic necessity is that the function must be unimodal. Function means the function which I am going to optimize must be unimodal in the given range, and it makes use of Fibonacci numbers. As we know, there is a well known sequence of Fibonacci numbers or Fibonacci, people are saying in that name as well. If we consider Fn is the sequence, that is the Fibonacci numbers, and we must be knowing that this is the series, this is the sequence we are getting 1, 1, 2, 3, 5, 8, 13, 21, 34, 55 in this way. If we just look at the sequence, we see it follows certain rules. The rule is that if I consider F0 is the first number, F1 is the second, F2 is the third in that way, and we see that F0 is always equal to 1, F1 is equal to 1. And if we consider other number, that would be sum of the previous two numbers. That is why Fn must be is equal to Fn minus 1 plus Fn minus 2. That is the beauty of the Fibonacci number. And we will use these numbers in the Fibonacci method. And there is one good thing for this method is that we have to say the total number of experiments before initiation. Total number of experiments or the total number of approximation we are making for optimal solution, that has to be said beforehand. And if this is so, now let us say this is my function, this is the given interval from A to B, and this is the function. As I said, function must be unimodal. Say we want to minimize the function, minimize f(x), and this is the range x. Then we are having the function minimize f(x) subject to x in between A to B. If we look at the graph, it is very clear that it has the minimum at this point. Let us say x star is the minimum for this function. Now, let me see another function, again also from A to B, and this is the function for us. Now, we see that function is having minimum at this point. This is my x star, this is the optimal solution for this function. Now, we want to implement one iterative process, that is the Fibonacci method for solving this minimization of f(x). If we just look at the property of the function, we see that function is having minimum here. That is why we can just have the interval reduction process in this way, that in the first iteration we will consider the initial interval. Say initial interval is A to B, and we will say this initial interval of uncertainty as L0. Now, since we are having a minimum here, in the next level we may just discard this part of the interval, so that in the next iteration we will just consider this interval, and in this case we will just discard, maybe we may discard this part. Now, that is why the basic philosophy of the region elimination technique is that, similar to Fibonacci method is as well, in every iteration we reduce a part of the interval, so that we will conclude, we will just complete, we will just conclude our iterative process with a shorter interval, with a small interval, where we will declare the optimal is lying in that interval. That is why the process is like that. We will start from initial interval of uncertainty L naught is equal to A to B. Now, my next process, my step 1, that is why is that for Fibonacci method is that, given the initial interval of uncertainty, let me just elaborate the iterative process. L naught from A to B. Now, as I said, this is the number of experiments must be said beforehand. Let the number of experiments be n. Once we are specifying the number of experiments, then since we are using the Fibonacci numbers, that is why we are sure that we will consider the Fibonacci numbers up to Fn. If we are having 5 number of experiments, then we will use the Fibonacci numbers F0, F1, F2, F3, F4 and F5 in that way. Just I will show the thing with the example in the next. Now, just let us go to the next step, that is step 2. What is my basic idea? Basic idea is that we will reduce a part of the given interval of uncertainty, that A to B. That is why the process tells us that we will consider 2 points, two experiments here, say x1 and another one is x2, in such a way that there is a specific distance of x1 and x2 from both the end of the given interval. In the next step, in the step 2, I will just show how to get the next approximations for the optimal solution x1 and x2. That is why to determine x1 and x2, what we have to do, that is initial 2 experiments, approximations will be defined in this way. We need to define one number, that is L2 star. The L2 star would be is equal to f n minus 2 by f n into L0. Here n is the number of experiments as we have specified before. That is why if it is n is equal to 5, then L2 star must be is equal to f3 divided by f5 into length of the initial interval of uncertainty, that is L naught. And why we need L2 star? Because what we will do, we will consider the interval A to B and we will just select x1 and x2 in such a way that both the experiments x1 and x2, these are all L2 star distance apart from both the ends of the given interval. That is the L2 star quantity. That is why once our L2 star is defined in this way, then we can generate 2 experiments, rather 2 approximations for the optimal solution x1 and x2. Therefore, x1 would be is equal to, since it is L2 star distance apart from A, x1 must be is equal to A plus L2 star. In other way, we can write A plus L2 star is equal to A plus f n minus 2 divided by f n L0. What about x2? x2 is again L2 star distance apart from B, that is why x2 must be is equal to B minus L2 star, that is equal to B minus f n minus 2 divided by f n L0. This is the basic thing, but we can do certain simplification for x2 here. How we can do so? We know L0 is equal to, that is the length of the initial interval of uncertainty. That is why we can write L0 is equal to B minus A. Once this is so, then we can write it down as 1 minus Fn minus 2 divided by Fn into B plus Fn minus 2 by Fn A. This again is equal to Fn minus Fn minus 2 divided by Fn into B plus Fn minus 2 can be written as we know Fn is equal to Fn minus 1 plus Fn minus 2. That is the nth Fibonacci number is the sum of two previous numbers. That is why Fn minus 2 can be written as Fn minus Fn minus 1. That is why we can write it down in this way. Once this is so, we can write it as Fn minus 2 again Fn minus 1 divided by Fn into B plus A, because Fn by Fn is 1, this is equal to Fn minus 1 by Fn into A. Thus, we are getting it as A plus Fn minus 1 divided by, I am sorry, A will not be there, Fn minus 1 into Fn into B minus A, yeah, plus A. Thus, we are getting A plus Fn minus 1 by Fn L0. That is why just look at the another form of x1, x2, this is my x1, A plus Fn minus 1 by Fn L0, and what about x2? A plus Fn minus 1 by Fn L0. In other way we can say this is as B minus Fn minus 2 by Fn L0. These are the forms of x1 and x2 respectively. How to adopt in the example I will just do in the next. Now, if this is so, what is my next task? If the function is like this, if this is my function, then certainly at point x2 the functional value is lesser than at point x1. If we consider the other way, this is A, this is B, and there are two approximations where x1 and x2 are lying between A to B. The function is like this. Certainly fx1 value, functional value at x1 must be lesser than functional value at x2. That is why in both the cases, if we consider the elimination technique, that is very clear. In the case 1, we will reduce this interval in the next iteration, because minimum cannot lie here, and if we consider the next case, case 2, then we must reduce this interval from x to b. That is why if we just consider both the things together, what is my next task? My next task is to find the values of fx1 and fx2, and by considering the unimodality property, we will reduce either A to x1, then my new interval of uncertainty would be x1 to b, or in the next case my new interval of uncertainty would be from A to x2. This is the case for both the cases. Now, that is why my next step would be, step 3 would be, we will reduce the interval L0 and we will rename the new interval as L2, as a new interval of uncertainty. That is why my new interval of uncertainty L2, that would be either, as we see from the previous case, either it is x1 to b, or it would be from a to x2 according to the functional value at x1 and x2. Now, what is the length of L2 then? What is the next interval of uncertainty length? Then certainly it would be from x1 to b or a to x2, and we will see the nice fact that L2 will be is equal to L0 minus L2 star, because we are reducing this length, that is L2 star length. This is the length we have considered x2 from b L2 star distance apart. That is why next interval of uncertainty, that would be is equal to L2, and this L2 would be is equal to L0 minus L2 star. What is L2 star again? Let me write it down. L2 star, that would be Fn minus 2 by Fn L0, and that can be written very nicely as Fn minus 2 by Fn L0, and the nice fact is that L2 would be is equal to Fn minus 1 by Fn L0. That is my next interval of uncertainty. Now, once it is fixed, then we will just find out the next approximation in the next step, step 4. That is why we will go for next approximation. If it is from x1 to b, we are having x2 here, then we will go to evaluate the next approximation x3 in the next. Now, to define x3, again we will have to evaluate L3 star. L3 star would be is equal to, as we have seen, L2 star is equal to Fn minus 2 by Fn L0. L3 star would be is equal to Fn minus 3 by Fn L0. Again, locate x3 in such a way that current two experiments are L3 distance apart from both the ends of the interval of uncertainty. Current two experiments are L3 start distance apart from both the ends of L2. This is my L2. That is why it would be from, that must be position of x3 in the next case. And if this is so, then again the same process, we will just repeat the process like previous. We will go to the step 5, we will evaluate the value, functional value at x2 and at x3, and assuming the unimodality property, we will discard a part of the interval. Unimodality property, discard a portion of the interval, L2, and obtain the new interval of uncertainty L3. And what would be the length of L3? Certainly, since we are discarding, this is L3 star, then the new interval of uncertainty would be L3 would be is equal to L2 minus L3 star. Again, if we just write down the thing in detail, that must be is equal to Fn minus 3 by Fn L0, and this is equal to Fn minus 3, that can be written as Fn minus 1 L2 as well. Then it would be must be is equal to f n minus 3 minus f n minus 1 divided by f n minus 1 L2, and this would be is equal to f n minus 2 divided by f n minus 1 L2, and this is the form of L3. If we look at the pattern of L2 and L3 separately, in L2 we got f n minus 1 by f n L naught, in L3 we are getting f n minus 2 by f n minus 1 L2. That is why in general, for obtaining the nth experiment, because as we got x3, in the similar process we will discard a part of L3 and we will reach to L4, and there also we will get another experiment x5. In that way we will proceed further and further. How long we will proceed? We will proceed up to the nth experiment. That is why if we consider the jth experiment, the formula would be, to obtain the jth experiment point we need to find out Lj star, as we got L2 star and L3 star, and that must be is equal to f n minus j divided by f n minus j minus 2 L j minus 1, and the corresponding length of interval of uncertainty after the jth experiment Lj would be is equal to, that is the length of the interval of uncertainty would be f n minus j minus 1 divided by f n L0. If I put j is equal to 2, we are getting f n minus 1 divided by f n L0. If j is equal to 3, then we are getting f n minus 2 divided by f n L0. In that way we can generate all the points x1, x2, x3 up to xn, and we will reduce the interval further and further, and at the end we will get nth interval of uncertainty, and the middle of that interval of uncertainty will be declared as the optimal solution for the given problem. Whatever I have said, let me just apply the whole process in one of the example. But one thing I must tell here, as I have said for other elimination technique, that there is one measure that is called the measure of efficiency of the elimination technique, because we have learned the exhaustive search technique, dichotomous search, interval search technique, and this is another searching technique, that is the Fibonacci method. In the next we will do the golden section method. For every method there is a measure for efficiency. In another name is that is called the reduction ratio, through which we can judge the efficiency of the elimination process, and I will discuss more on this. But here just I want to tell you the measure of efficiency or the reduction ratio can be defined as ln minus L0, where ln is the length of the interval of uncertainty after nth experiment, and L naught is the initial interval of uncertainty. Now, this is the thing. Now, let me apply this process for one example. The example is that find the minimum value of f x is equal to x square plus 2x within the interval minus 3 to 4 using the Fibonacci method. And obtain the value, optimal value within 5% of exact value. Now, this is the problem for us. Now, we want to minimize the function x square plus 2x within the interval minus 3 to 4. If we just draw the function, we will see the function is very much unimodal within minus 3 to 4, and function is having a minimum somewhere in between minus 3 to 4. And there is one restriction is that we want to have the optimal value within 5% of exact value. We need to use the Fibonacci method. As I said, the first necessity function must be unimodal, that is true here. The second is that the number of experiments must be specified beforehand, but there is no information as such about the number of experiment, but we can deduce it from the given desired accuracy. That we want to have the accuracy 5% accuracy of the exact value, 5% of the exact value. That is why if we say ln is the interval after nth experiment, if this is my ln, then mid value will be declared as the optimal value I said. Then if we want to have the 5% of the exact value, then the half of the nth interval of uncertainty must be less than is equal to L naught into error percentage. That is why we can write it down that what is my objective? My objective is to find out the number of experiments from the given, from the level of desired accuracy, length of final interval of uncertainty after nth experiment divided by length of initial interval of uncertainty must be less than is equal to 5%. That means actually we are considering half length of the interval of this is must be is equal to 2 into this. That is why this must be is equal to 5 by 100. In other way we can say as ln by 2 must be less than is equal to 1 by 20 L naught, or we can say ln must be is equal to less than is equal to L naught by 10. One nice fact of Fibonacci method is that, as I said, the measure of efficiency ln by L0, that is after the nth experiment, if ln is the interval of uncertainty, L naught is the initial interval of uncertainty, always we will see for any number of n, whatever number of n we will choose, we will see ln by L0 always will be is equal to 1 by Fn. If we consider n is equal to 5, it would be 1 by F5. If we consider n equal to 6, it would be 1 by F6. That is why other way we can say that this measure, this reduction ratio can be used for selection of the number of experiments if it is not given to us. That is why we can say that ln by L0, that is equal to 1 by Fn, must be less than is equal to 1 by 10. What exactly we are getting? Fn must be is equal greater than equal to 10, and we know F0 is equal to 1, Fn is equal to 1, F2 is equal to 2, F3 is equal to 3, F4 is equal to 5, F5 is equal to 8, F6 is equal to 13. That is why we can conclude here that since Fn is greater than equal to 10, that is why we can say n must be greater than equal to 6. This is my conclusion. That is why from here we can say the minimum 6 number of experiments we have to do for getting the desired level of accuracy, that is the 5% of exact value. As we have considered the middle point of ln as the optimal solution of the given problem. That is why we are concluding from here that the minimum number of n must be 6. If we just increase the number of n as 7, 8, etc., then we will get better and better result. That is why the interval of uncertainty will be smaller and smaller further. But since we are doing it manually, that is why we will restrict ourselves to value of n as equal to 6. We will apply in the next the iteration process from step 1. What is my step 1? Initial interval of uncertainty is given for us. That is why step 1 would be is equal to L0 would be is equal to from minus 3 to 4, and my n is given, we are considering n is equal to 6. Now, step 2, we have to obtain two approximations x1 and x2. Now, for that thing, as I said in the algorithm, we have to generate L2 star. How to get L2 star? L2 star must be is equal to Fn minus 2 divided by Fn L0. What is my Fn minus 2 here? My n is equal to 6. That is why it must be is equal to F6 by F4 by X6 L0. What is F4? F4 equal to 5. As we have seen, F4 equal to 5 by 13 into L0, the length. Here length is coming as 7. That is why we will multiply with 7, and this value we will get 2.6923. Once we are getting L2 star, we will generate two experiments, x1 and x2 in the next. How to get x1? As I said, if I just consider the interval a to b, that is from minus 3 to 4, then x1 and x2 we will generate in such a way that both the experiments will be L2 star distance apart from both the ends. That is why x1 must be is equal to minus 3 plus L2 star, that is 2.6923, and we are getting x1 is equal to minus 0.3077. And if we consider x2, we will get 4 minus 2.6923, and that would be is equal to 1.3077, that is 1.3077, and function is unimodal in between. That is why our next task is to find out the functional values at x1 and x2. What is the functional value at x1? Let us see, before to that let me see the functional value at both the ends. If we consider here, the functional value will come as 3 and fx will be 24 at 0.4. At x1 we will see the functional value is coming, fx1 is coming as, oh that is minus, not in the positive side, that is in the negative side, minus 0.5207, and x2 value is coming, fx2 value, that is coming 4.3255. If we just write down the functional values here, fx1 would be is equal to, we know the function is x square plus 2x. If we just substitute the x1 value there, we will get fx1, that would be minus 5207, and fx2 is coming as 4.3255. What we see that fx1 is lesser than fx2. Since the function is unimodal, the maximum, I am sorry, this is the minimization of the function. The minimum cannot lie within this, because the functional value, the function is coming like this only. That is why minimum will be in the within the interval from minus 3 to x2. That is why we are discarding. This is the conclusion, that discard x to 4 and obtain the new interval of uncertainty, obtain L2, that is the new interval of uncertainty from minus 3 to x2. Coming to the next, step 3. We will get L2 as we have considered L2 is equal to minus 3 to x2, that is means minus 3 to 1.3077. If we consider, if we just apply the formula we have learned, just now learned, we will get the same value for L2. How? As we know L2 is equal to L0 minus L2 star. What is L naught? That the length of L naught was 7. Whenever I am writing L naught, L2 star within the equation, it means that this is the length of the given interval, and L naught is 7. And what about L2 star? Just now we got L2 star is equal to 2.6923, and that is coming as 4.3077. If we just see the interval size here, it is coming 4.3077. And again there is another nice fact is that we can get L2 in this way as well, as we got that L2 is equal to Fn minus 1 by Fn L0. What is Fn minus 1? That is my F6, that is my F5, L0 is 7. This is another formula for L2. This is coming as 8 by 13 into 7 is equal to 4.3077. That is a nice fact. This is the beauty of the Fibonacci method. If we apply this, if we just consider this one, it is coming the same value, here also the same value, because we are considering here the Fibonacci numbers. But the basic idea is that now in the next we will consider the interval from A to x2. What is my A? That is minus 3, my x2 is 1.3077. In between there is a point we are having, that is x1. My x1 is equal to minus 0.3077, that is my x1. Then what is my next step? Next step would be is equal to obtain the next approximation for the optimal solution, that is x3. For getting x3 again we need to generate L3 star as we have done before. L3 star is equal to Fn minus 3 divided by Fn L0. What is Fn minus 3? This is F6, this is F3, L0 is again 7 here, and F6 is equal to 13, and this F3 is equal to 3. That is why 3 by 13 into 7, this value is coming 1.6154. Once we are getting so very nicely, we can select x3 in such a way that the current two experiments, that is the experiment one is x1 and another one is x3, that would be L3 star distance apart from both the ends of the given interval. And if we just see the fact, x1 is L3 star distance apart, because if I just consider the length of the interval from x1 to x2, always it would be is equal to 1.6154. That is why we have to select x3 here, that where x3 would be L3 star distance apart from one end. And in this way we will get x3 is equal to my A plus L3 star, that is minus 3 plus 1.6154, and it will come as minus 1.3846. And if we just find out the functional value at this point, we will get the functional value as minus 0.8521. Now let us see what is happening in the figure. And if we see again at point minus 3 the value is coming 3, at point x2 the value is, we calculated the value is 0.4325, at point x1 the value is coming minus 0.5207, at point x3 the value is coming minus 0.8521. What we see again? Again we see that fx3 is lesser than fx1. That is why what is my conclusion? Discard this interval. From optimum cannot lie within this, because minimum should lie within this interval. That is why discard the interval x1 to x2, and we are getting new interval of uncertainty L3 as minus 3 to minus 0.3077. That is why let us go to the next step, step 5. I am sorry, this is not the step 5, this is page number 8, and we are going to step 5, and we will get L3 equal to L2 minus L3 star. My L2 was the length of L2 rather 4.3077 and L3 star just now we have calculated 1.6154, that is why the length is coming 1.6923. If this is so, then we are reaching to the next interval. This interval L3 interval will be from minus 3 to minus 3077. What is the next task? Again the next task would be to find out the next approximation. We have to reach up to 6th experiment because we have considered n is equal to 6. That is why we are moving to the next. We will obtain x4. Let me draw the figure again. We are having minus 3 in one end, minus 0.3077 at x1 in the other end. This is my A. In between we are having x3 and this value is x3 is equal to, just now we got that is minus 1.3846. Now to obtain x4 again we need to find out L4 star, that would be is equal to Fn minus 4 divided by Fn L0. Let me just calculate the entire thing very quickly. That would be F2 into L6 into 7, that will come as 1.0769. If this is so, again the same thing is that both the current two experiments must be L4 star distance apart from both the ends. That is why we will consider the next, that is x4 as minus 3 plus L4 star and it would be is equal to minus 1.9231 and here must be minus 1.9231. Again we will see the functional value at x4. We will see the function, we see the functional value is coming as minus 1.1479. What we see the figure here again? Here it is 3, here it is minus 0.5207, here it is minus 0.8521 and here at x4 the value is coming as minus 0.1479. What we see again? We see that Fx3 is lesser than Fx4. Then what is the conclusion? Discard the interval from minus 3 to x4. Minus 3 to x4 means we are discarding this interval in the next. That is why the new interval of uncertainty, that is my L4, will become as from x4, that is minus 1.9231 to minus 3077. We have to repeat the process again. Let us go to the next. We have to have more number of experiments, then only we will get better result. We cannot start with n equal to 2 or 3. This is a process. If we just automate the process is very easy, but if we just do it manually, it takes time. L5 star. L5 star again would be is equal to Fn5, Fn minus 5 by Fn L0. That would be is equal to 1 by 13 into 7, that is coming as 5385. Therefore, we will again consider the interval from x3 to x1, that was minus 1.9231 to minus 0.3077, that is my x1, that is my x3 here. In between we are having x4, no, that is my x4, we are having x3 in between, x3 is coming somewhere. Now, we will calculate x5. Again the same logic, current two experiments, that is x3 and x5 must be L5 star distance apart from both the ends. If we see that it will be always this is L5 star, that is why x5 must be here somewhere. That is why we will consider x5 is equal to minus 0.3077 plus L5 star. that is 0.5385. If we consider, we will get x5 is equal to minus 0.8462. This one x3 was minus 1.3846 and we are having x5 as minus 0.8462. This is minus. And we will calculate the functional value at x5 and this value is coming 0.97. We are taking a large number here with more decimal points because we will see why we are considering in the next, because once we will go to x6, that will be very close to x5 in the next we will see, and that is why we will see that in the next case functional value will differ with a small amount. That is why we are considering a more decimal points in this case. And here we are having x4. This is my x4. Now, let us see the functional values at every point. At x4 it was minus 0.1479. At x3 the value was minus 0.8521. At x5 the functional value is more, that is 0.97634 etc. 4556. And at point x1 the functional value is minus 0.5207. Again the same conclusion, since the function is a unimodal, fx5 is lesser than fx3, therefore optimal cannot lie in this area. That is why we will discard this interval and we will get the next interval L5 as minus 1.3846 to minus 0.3077. Alright, and in between how many points we are having? From the previous one we are having x3, we are having x5. Let me write down the values here. 1.3846, my x5 was minus 8462, my x1 was minus 3077. We need to get x6 because that is my last approximation. Let us see what is happening in the next. We will consider L6 star, that would be Fn minus 6 by Fn L0, that is again F0 by F6 by into L0, that is why it is again 1 by 13 into 7, that is why the L6 star value is same as the previous value. Always we will see the last Ln star would be is equal to Ln minus 1 star always, if the n is the number of experiments. If this is so, then we will say the same thing, that the current two experiments would be L6 star's distance apart from both the ends. That is why x6 would be is equal to x3 plus L6 star, and we will get this value as minus 8461. And what is the functional value at x6? We will see the functional value is coming minus 0.9761. Just see with the fx5, 631,479. That is why what we see, we are getting x6 here, that is minus, this is my x6, 8461, and we are having lesser functional value, higher functional value than x5. That is why what is the conclusion in the next? Since this is high value, considering the unimodality condition, again we will discard this part of the interval and we will declare that the final interval of uncertainty L6 would be is equal to from minus 1.3846 to minus 0.8461. This is the, and the middle point of this interval will be declared as the optimal solution for this interval. Now, there are few things to be noted here. The first thing is that always we will see that xn minus 1 is almost same as xn, and only the difference will be there in the decimal in the higher decimal points. This is almost same with xn is same as xn minus 1. And another nice fact is that always we will see that ln by L0, that is my reduction ratio. That value here, if we see the ln distance, this distance will be is equal to 5385 and L0 is my 7. This is equal to, we will see 0.0769, and that would be is equal to 1 by Fn. What is my n here? N equal to 6. That is why it would be 1 by F6, rather this would be 1 by 13. That is the nice fact of the Fibonacci method. Always we will get this one. For whatever n value we will consider, irrespective of the value of n, we will get the same result here. Let us move to the next problem, and this is our maximization problem. Let me do the problem very quickly, because I will just write down the steps without going into detail about the calculations. My problem is that maximize fx x by 2 for x lesser than is equal to 2, and this is minus x plus 3 for x greater than 2. We must see the pattern of the function. Pattern of the function is very small here. I am sorry, the pattern of the function is that function is not really continuous, and we need to maximize within the interval 0 to 3, and using the Fibonacci method. And another thing is given here, that number of experiment has been specified, n is equal to 6. All right. For starting the process, again we will do the same process. We will consider A and B, that is 0 to 3. We will consider L2 star, and we will find out x1 and x2, L2 star distance apart from both the ends. And we will see x1 will come as 1.8462, x2 will be 1.1538. We will find out the functional values at both the points here, and we will see the functional value will come, just you calculate, we will see this will give you the value f1 is higher value than f2. Since the problem is the maximization problem, that is why the discard process is the reverse to the minimization problem. Here we will not discard the higher value, we will discard the lower value. That is why this would be this one, this is the higher value, and we will discard this interval in the first case. And we will move to the next. We will calculate L3 star, and once we will calculate L3 star, we can generate x3. x3 would be is equal to 2.3076, and this is my interval, and we will place x3 in such a way that it would be L3 star distance apart from both the ends, and we will see that x3 will be, I am sorry, this is x2 and this is coming x1, and if this is so, we will consider x3 here, and we will get the functional value, and functional value will again we will see that fx3 value is lesser than fx1 value. In that way we can complete the whole process. Let me write down the approximations only. x1, x2, x3, x4 is coming as 1.6152, x5 is coming as 2.0768, and x6 ultimately will come as 2.07696. And if we just apply the same process, this initial interval of uncertainty will reduce at the end to 1.462 to 2.07696. That would be L6 rather, because we are doing the 6 number of experiments altogether. Here the length of L6 is coming again 0.23076, and here also we can just see the same fact that ln by L0, that is the L6 by L0 in that case, this divided by 3 is equal to, we will get 0769, the same value 1 by 13, 1 by F6. The intercalculation anybody can do just like the previous problem, just only thing just I wanted to mention here that for the maximization problem, if we just consider that unimodality property, instead of considering the lower value of function, we will consider the higher value of function in the selection, and that is why the discard, the elimination of the interval will be according to that, and in that way we will reach to the final interval of uncertainty, that would be much more smaller length, and that can be declared as the final interval of uncertainty, and middle value of that final interval of uncertainty will be the optimal solution. Fibonacci method is very efficient method for getting optimal solution for nonlinear programming problem, even for discontinuous function. That is all for today. Thank you.